Hello again. So this is part 2 of finding the derivative of e to the x. And so we've sort of set up the definition of the derivative, simplified things as much as we can, and we've gotten to this point right here, that the derivative is going to be e to the x. We were able to pull that out times whatever this thing is, this limit. And if we were to just plug in 0, we'll get 0 over 0. So obviously, we've got some work to do here. But we realized at the end of the last video, this represents something nice. This is actually the slope of the tangent line to this function y equals e to the x, specifically at x equals 0. So what we're going to do now is explore the graph of this and see if we can figure out what the slope should be. And then if we find it, if we're successful, we can finish this derivative. So in order to start, we want to think about the number e. And so to remind you, e is this number that kind of goes on forever. So that's why we use the symbol e to represent it. There's no possible way to list out every single digit. Like, you just cannot do it. So e is how we capture every single digit, so we know it's the exact value. But if you want to know, like, okay, well, where is it approximately? E is 2.17281828459045, and that's as many digits as I remember. But if I put the ... that's implying it keeps going. So clearly e is approximately like, oh, you know what, I messed that up, sorry. It's 2.71828. I don't know why I added the extra one in there. So 2.72 is where most people leave it. Similar to how pi, we kind of approximate it to 2 decimal places as a useful calculation. You can think of e as around here. So clearly e is between 2 and 3. It's closer to 3, but it lies somewhere in the middle. Okay, so we're going to explore exponential functions with these bases, meaning we're going to look at the graph 2 to the x, we're going to look at e to the x, we're going to look at 3 to the x. And as we look at the 3 of them and sort of compare tangent lines, that'll kind of help us figure out, well, what's really going on at e to the x, which is the one we care about. Okay, so I'm on GeoGebra, and I'm just going to type in, we're going to start with 2 to the x, because that was like in order of least to greatest. That's the first one we deal with. So y equals 2 to the x. Okay. So we have this exponential function, and we're trying to find the tangent line at 0. So we can see at x equals 0, we have this point right here. So the tangent line is going to be maybe something like that. It's not necessarily the best sketch, but something like that. And from way out here, it's really hard to tell what the slope of that is, especially because what if I drew it slightly off, right? Like, I could just tweak it a little bit and it would change my calculations if I was going off my drawing from here. So we're going to zoom in. Oops. All right, so if we zoom in, and I want to zoom in really, really far, because the closer I get, the better my approximation is going to be. Okay, so I think this is pretty close. We can see like I'm really close to the value 1 because above it is 1.00005. Obviously I could get closer, but this is good enough for us. And the reason I say that is my line already kind of looks linear now, even though I know I'm not dealing with a line. I have an exponential curve, but at this point that I'm zoomed in, it looks like a line. So if I could imagine the tangent line here, it would probably look exactly like this. So let's try to calculate the slope of this line. So we can maybe count like the small, so this looks like it's going up to over 3, up to over 3, up to over 3. That one's just missed it. Yeah, it's not quite 2/3, but it's like kind of close to 2/3. Okay, so that means that I'm just going to write a little note here that the slope of this tangent line is approximately 2/3. Again, not exactly, but that's close enough for now. All right. So now let's go ahead and look at the other end of our, I guess, experiment, right? So we're doing 2 to the x, e to the x, and 3 to the x. Let's look at the other side of b and explore the 3. All right, so if we compare the graphs of these two, we can see that the blue, which is 3 to the x, and then the green is 2 to the x. We can see that they both have the same intersection point, but after x equals 0, as x gets larger and larger, the blue curve is growing faster, which hopefully makes sense because this was a larger base. Okay, so now let's go ahead and zoom back in. And we want to zoom in around at this point. Okay, so had to adjust that because it looked a little different. But if you remember when we had 2 to the x, it looked like it was about 2/3. So up 2 over 3, up 2 over 3. So I made the note here. That was for this function. Now we're looking at 3 to the x. So again, go ahead and calculate what the approximate slope would be. So this looks like it's like up 3 and then over, really close to over 3, but it's just short. And then if I go up 3 again, it's like even shorter than before, but it's still around over 3. So this is like almost up 3 over 3. So it's like close to 1, but it seems to be a little maybe a little steeper than 1. So I'm going to put that on here, like the slope is like maybe like 1.1-ish, just a little bit bigger. Okay. Okay, so now let's get into the function we actually care about, which is e to the x. Now we can see that e to the x does land right in between the other two functions, and hopefully that makes sense because e is between 2 and 3. It's much closer to 3, and this curve definitely is much closer to the 3 to the x curve than my 2 to the x curve. And we're going to zoom in on this function and do the same thing we did for the other two. All right, so I'm zoomed in, and here's the 2 to the x, which was our slope of about 2/3. Here's our 3 to the x, which, you know, is a little bit steeper. And we said it was just a little bit steeper than 1. That's why we said maybe 1.1-ish. So based on those two approximations, you could maybe guess what e to the x could be, like what the slope of this tangent line would be. And go ahead and count the boxes and see if you could figure out what it is. Pause if you need to. And when you think you got it, you can hit resume. Okay, so this function, if I look at these, do you see how this looks like it's going right through the diagonal, or the corners, right? Like this diagonal line is hitting every corner of these minor grid lines, which looks like it's up 1 over 1, up 1 over 1, up 1 over 1. And, you know, we might say, well, how do we know if it's going exactly through? But the fact that it looks the same consistently sort of telling us it probably is going exactly through, but you could always zoom in a little bit more if you wanted to be sure. So, sorry, let me zoom in a little bit here. I'm gonna go in really far here. What do we think? Does that look like it's still up 1 over 1, up 1 over 1? I think it kind of does. So this slope of the tangent line is looking like it's, I mean, because maybe we're not sure, we could say approximately 1, but based on what we see, it looks like it's exactly 1. It didn't change ever. Like in the other two examples, it was like, oh, up 2 over 3, up 2, oh, a little bit short, up 2, oh, even shorter. Same with the 3 to the x, like the slopes seem to kind of change, and that's why we put approximations. But this one doesn't look like it's changing. It looks like it's consistently up 1 over 1 every single time. And so the good news is that this is actually true. The slope of the tangent line to y equals e to the x at 0 is 1. And it's actually the only exponential function that will have that slope. 2 to the x doesn't have it. 3 to the x doesn't have it, right? It's closer, but it's not it. We could do like 2.8 to the x. It won't be exactly 1. We could do 2.72, won't be exactly 1. E is the only number, right, the only base that will get us a slope of exactly 1. And this is one way many people actually define the number E. So the definition of E could be thought of as, well, it's the only number whose base to an exponential function has a tangent slope of 1 at 0. So if you go to the packet, let me pull that up, you'll notice this page called the definition of E, and that's exactly what we were just talking about. That E is the number, so that this thing, which is the slope of the tangent line at x equals 0, this equals 1. E is the only number that will get that. So is the only one whose tangent line, right? This function is the only one with a tangent line at that x equals 0, which was the 0.01 on all of the exponential functions that we looked at. But it's the only one whose slope, which you can think of as f prime, that is exactly 1. So I know that this, is a different definition, but it's actually kind of neat to think about that, like, that's a very special base. And because now we know what the slope of the tangent line is, we know that this limit equals 1. So we should be able to finish our derivative now. So this is where we left off. And this limit was the thing we just explored, the slope of the tangent line, which we now know is actually 1. And so my derivative is just e to the x times 1, which is e to the x. So the derivative of e to the x is like itself. It's just a copy. And that's it. Yay. Okay, so now we have another derivative. You don't have to do it the long way anymore. We already know, we've proven that the derivative of e to the x is e to the x, and this is just another like rule in your like toolbox. So if you ever see derivatives pop up, like, let's say we had y equals 2e to the x. We could find the derivative of that. We have a coefficient 2, and we have e to the x. Go ahead and pause and see if you can come up with the derivative. Okay, so if this is the coefficient, this should just stay. And then we have e to the x, but the derivative of e to the x is e to the x. Okay, thank you for watching. We're going to do more practice when we meet in class again. But if you have any questions, please make sure to write them down and ask when we see each other. Okay, thanks for watching. Bye.